What's going on, smart people? Bringing you another episode of Tensor Calculus for Physics, and today we are wrapping up the differential operators, specifically curl. How do we express curl in the language of tensors? This gets its own video because there are some special considerations that you have to make that make it a little bit different from how we approach divergence and the Laplacian. And I'm going to be doing this in a different way than is approached in the book being around here somewhere. It's Tensor Calculus for Physics by Dwight Neuenschwander. He mentions in the beginning of the book that this is not going to be the most formal treatment of tensor calculus, and I think that really is the case for how he approaches curl. So we're going to approach it in a bit more of a formal way, but probably more of the middle ground. Anything that I don't necessarily derive in this video, I will leave links in the description so that you can look into it for yourself, and it'll be completely self-contained. But anyways, curl, let's get into it. So for divergence and the Laplacian, we've been following the same prescription where we, instead of ordinary vectors, we write down covariant or contravariant vectors, and derivatives are replaced with covariant derivatives. The reason curl is a little bit different is because of how we express it in index notation to begin with when we're not even thinking about tensors, really. So curl of a vector A we could express as del cross A, the ith component, so that could be x, y, you know this by now. And I'm going to put a little tilde on top of the vector, which means it's the ordinary vector. It has nothing to do with contravariant, covariant stuff just yet. This is equal to epsilon ijk. In Cartesian coordinates, say it would be dj ak. Okay, and we want to tensorify this. We want to make this generally covariant. So normally we would promote derivatives to covariant derivatives and vectors, to covariant vectors. But what do we do with this guy? What do we do with this Levi-Civita symbol? Well, there's a reason it's called a Levi-Civita symbol. It's because it's not technically a tensor. It's what's referred to as a tensor density. So before we go any further, I'd like to revisit that topic briefly. Okay. So what is a tensor density? We went over it in, I think it was video 8, but we came across our first instance of it when we were defining the determinant of the metric in the Jacobian. For the Jacobian, that was equal to the square root of the ratio of determinants of the metric. So the determinant in one coordinate system divided by the determinant in another. So let's put a prime here. And if we solve for root g prime, we get that root g prime is equal to 1 over the Jacobian times root g. What this tells us is that the determinant of the metric, or the square root of it to be specific, is not a scalar necessarily. It's what's referred to as a scalar density or a tensor density, because it's not equal to itself in a different coordinate system, but rather it's weighted by some Jacobian raised to a certain power. So any object that almost transforms as a tensor of a given rank, but times a certain power of the Jacobian, that is referred to as a tensor density. And the weight of the tensor density is the power that the Jacobian factor that shows up in the transformation rule is raised to. So in this case, the weight would be -1. Now, why does this tensor density stuff need to be discussed? Well, the way that I like to think about it, and this is just like a very special case, so don't take this as across the board. But if you were to say, suppose you have a tensor Tij, and it can be expressed in terms of an integral of a tensor density, tau ij, times the integration measure. That's dn, n-dimensional integration measure. Well, we know that integration measures, these volume elements, aren't scalar. They transform when you go to a different basis. Specifically, in a new frame, d prime xn would be equal to the Jacobian times dxn. So since this is not scalar, the object that's inside of the integral must also not be a tensor in order for the combination of them to have a chance at becoming a tensor. So in this case, Tij is not a tensor, it's a tensor density, not a tensor. But say we're going from Cartesian to spherical coordinates or something, or Cartesian to something else. Then this g prime, which is going to be our Cartesian coordinates, our Jacobian just ends up being root g then, because the determinant of the metric in Cartesian coordinates is just 1. So we would get that root g times tau ij would be a tensor. Okay, and that's so that we can impose that the integral over everything is a tensor. So we're absorbing the non-tensorial nature of the integration measure into the tensor density. That way, that product of the two will give us a full-fledged tensor. Okay, and this is the exact same thing that ends up happening with the Levi-Civita symbol. So the Levi-Civita symbol in a given reference or in a given basis, let's say epsilon ijk, it wants to transform as a tensor. Epsilon, let's say L and M, and then all of our derivatives, dx. Okay, what do we want? dxL,
dxi, dxn, dxj, dxm,
dxk. So it wants to do this, but it transforms via this factor of the Jacobian out front. This is something that I'm not proving here. I'll leave a link in the description so that you can see where the transformation law for the Levi-Civita symbol comes from. It comes from the notion of determinants. But just so that you know, not all of them just have a weight of 1. But in this case, the Levi-Civita has a weight of 1. So it is not a tensor, it is a tensor density. So then we say, okay, well, how do we even begin to express curl in this covariant form if not everything we were working with to begin with were full-fledged vectors and tensors? Well, we can do that by noting how the determinant of the metric, the square root, transforms, and the Levi-Civita symbol transforms. Individually, neither of them are tensors or scalars. However, the product of the two, we get that 1 over j will cancel with the j, and we recover the transformation rule. So we will take as our prototype, our new definition of what's called the Levi-Civita tensor to be, I'm going to call it E ijk, ooh, you can do better than that, is equal to, or it's defined to be, root g times epsilon ijk. So this is going to be, this is a full-fledged rank 3 covariant tensor. So this is a tensor. This is a tensor. Nice. Hooray. Now, for the purpose of this video, I've already gone through it. A little spoiler ahead. If we want to promote derivatives to covariant derivatives and all that good stuff, it turns out that it's much easier to do if we let these vectors be covariant vectors and the Levi-Civita tensor be the contravariant tensor. So what we just wrote down, it's a tensor, so we can raise its indices. But one might be tempted to keep that in covariant and have contravariant derivatives and vectors. That ends up being a lot messier, so we're going to instead define the contravariant Levi-Civita tensor, E upstairs ijk, which is going to be equal to 1 over root g epsilon upstairs ijk. Now the upstairs notation for the epsilon is just a notational convenience. That way we can employ Einstein's summation convention, one upstairs with one downstairs when doing summations. Numerically, the upstairs and downstairs are exactly the same for the epsilon terms. The reason the contravariant Levi-Civita tensor gets the 1 over root g is so that once you fully contract the tensor, you get a scalar. But since the root g's aren't scalars, we need a 1 over so that they cancel, and you do in fact get a scalar. Okay, so this is what we're going to be working with. So now we can finally implement our usual prescription for promoting vector calculus operators to things that are more covariant. So we are going to define, we're going to say we have 3 upstairs indices and we're going to have 2 downstairs indices. So the object that we're going to define is going to be a contravariant vector, and it's going to be the contravariant vector of the curl, component of the curl. So I'm going to call that Ci is equal to E ijk covariant derivative of the jth coordinate and then the kth component of the covariant vector A. Let me make sure that I was putting tildes on my A's up there. Yeah, I was. Okay, cool. So up here, this is an ordinary vector. That's what you would use in any classical or Griffiths E&M stuff. Now I'm making the distinction between covariant and contravariant vectors. Okay, so let's go ahead and write this out. So this is equal to 1 over root g epsilon I j k dj ak. Perfect. So in essence, we're kind of done here. Now it's a matter of simplifying, and we'll do an example to see if we can recover components of the curl that are familiar to us already. But we can express this a little bit better in a better notation. The role of the Levi-Civita tensor is it anti-symmetrizes other tensors. So if we write this out, let's suppose ijk is cyclic. That's a cyclic permutation. If this is the case, and we're summing over j and k here, then we get that c superscript I is equal to 1 over root g epsilon ijk dj ak plus epsilon ikj dk aj. One important fact about curl and cross products in general is they really only have a very limited use in anything outside of three-dimensional space. So throughout this video, we are assuming that I, J, K run from 1 to 3, okay, which is very important. So that's why I'm writing it in this following way of I, J, K and I, K, J, because we can't have any of the indices be equal, and now we can use this whole, if it's cyclic, you get a 1, if it's anti-cyclic, you get a -1. So this epsilon ijk is going to give us a 1, ikj is going to give us a -1. So this is equal to 1 over root g dj ak minus dk aj. So we started out on the right-hand side. We have this third-rank tensor here and this second-rank covariant tensor here. And what we're left with after applying the tensor is this anti-symmetrized version, because this should be equal to minus 1 over root g, 1 over root g dk aj minus dj ak. So it anti-symmetrizes the tensor. Usually when you anti-symmetrize a tensor, you divide by that factor of 2, and that would actually pop up if we wanted to express this curl component by projecting out the component from this tensor. But anyways, let's get rid of this term here. Now that brings up an interesting point, because on the left-hand side we have a contravariant vector, the component of a contravariant vector, and on the right-hand side we have j's and k's instead of I. So the notation is a little bit weird here, so sometimes you may see this absorbed into a new quantity. We have two indices downstairs, that is a full-fledged tensor, so you may see that referenced as a 1 over root g ckj, a contravariant tensor, which is antisymmetric. Future Andrew here, just want to address a typo real quick. I should have written CJK, and the 1 over root g should have been absorbed into it so that it stays a tensor. Anyways, back to the video. So when you write down things like field strength tensors in E and M, where you have the IJ, the 1 through 3 components, that's why you write it in terms of that derivatives acting on the vector potential, that difference. It's because you can write those cross products in terms of components of a second-rank tensor, which is pretty interesting. Okay, but we can simplify this a little bit more. So if we want to write down the covariant derivative, so this is equal to 1 over root g dj ak minus gamma, let's call it, I don't know, L jk al. So that's the covariant derivative acting on this vector here. You get a minus because you're acting on a covariant vector, minus the covariant derivative, minus dk aj, minus minus, that's plus gamma L kj al But remember, gamma L jk is equal to gamma L kj. It's because the symmetric tensor is symmetric, and this is defined in terms of derivatives of the metric tensor. So these connection coefficient terms actually cancel. And we're left with the ith component of the contravariant curl vector is equal to 1 over root g dj ak minus dk aj. There we have it. Now this is a contravariant vector regardless of if we relate the covariant a's to the ordinary vectors. We understand that the contravariant curl vector should be related to the ordinary one by dividing by that metric component, the square root of that metric component, ci. There we go. So once we do an example, we'll have to keep that relationship in the back of our mind, that what we're calculating is the component of a contravariant vector. I think that that's fascinating, though, that those connection coefficients end up canceling out, though. But let's go ahead and do an example. So let's do an example. Let's do spherical coordinates, because why not? And let's do just one component. Let's not do all three, but let's not do the r component because h is 1 in that case. So you might be tempted to identify the contravariant vector exactly with the ordinary vector because you'd be dividing by 1. So let's pick on c theta. And for perspective, our a cyclic permutation would be r, theta, and phi in a right-handed coordinate system. Okay, now I already kind of gave it away up here, so let's go ahead and snag what we know the answer is and see if that's what we end up getting. My issue with how the book does it is you get this answer at the end, and then you kind of like pattern match with what we already know the answer is. So you could be like, oh, if we multiply by this factor, you get the final solution that you want for the regular curl. And you randomly get these 1 over root g's and stuff from everywhere because you never took the consideration to say, oh, we need to promote this guy to a real tensor as opposed to a tensor density. So the fact that we are being more careful is going to help us. Okay, it came out. I'd probably just said the most obvious statement ever just now. The fact that we're being careful is going to help us, yeah. Okay. So let's go ahead and apply the magenta equation in spherical coordinates. So we are looking at c theta and that's going to equal 1 over root g. In spherical coordinates, we've done it a million times now, root g is r squared sine theta. So it's going to be 1 over r squared sine theta. Now we need to do our coordinate derivatives. So if we're looking at the theta component, then a cyclic permutation would then be phi, so theta, phi, r. So if this would be I, j, k. So dj would be dd phi acting on ar, where this is still a covariant vector, minus dk would be d over dr a sub theta, right? Sorry. What am I looking at? J is phi. Okay. Now let's do the conversion from covariant to ordinary vectors. So we know a mu, where that's a covariant vector, is equal to h mu times the ordinary vector. And in spherical coordinates, h mu is 1 r sine theta, which is the square root of those metric terms. So we can express this in terms of the ordinary vectors. This is equal to 1 over r squared sine theta d over d phi 1 times a sub r tilde minus d over dr r sine theta a phi tilde. Okay, so I'm going to go ahead and distribute the 1 over sine theta inside. So this is going to be equal to a 1 over r squared 1 over sine theta dA sub r tilde over d phi minus, that cancels the 1 over sine theta in this derivative, so it's minus d over dr r a tilde phi. Now, is that equal to what we got in blue? It shouldn't be, right? We know that it should be equal to it, divided by our h mu, and we see that it is exactly equal, but we get this 1 over r term, this extra 1 over r term. Now we're looking at c sub theta, so we know c theta, this is a contravariant vector, c theta should be equal to 1 over h theta, the ordinary vector. So if we multiply what we just got here by h theta, we should get our ordinary vector. So h theta is equal to r. So h theta times c theta, one of those 1 over r's cancels, and you get 1 over r, 1 over sine theta, d over d phi, ar tilde, minus d over dr, r a phi. So it checks out. Cool. So we've successfully built a full-fledged contravariant vector that is related to the ordinary vector by the usual prescription. That lets you know that we did it right. If we got additional prefactors like you do if you just follow the book, then you're wondering where all of these root g's are coming from. So we successfully built our vector. This is how you can relate it to the regular curl component, and this will work in any coordinate system that you'd like. So there you have it, folks. If you ever want to calculate the curl in a certain coordinate system, but you don't feel like memorizing them all, you can just use this equation, which is just weighted by this 1 over root g, and you can relate it to the ordinary vectors by dividing by that h mu, just as usual. So I hope you guys enjoyed this video and found it a little bit useful. In the next videos, I'm excited because we're kind of leaving just the strictly math part, and we're getting into something a bit more physical. So in the next videos, we'll be talking about curvature. So look forward to that. So again, I hope you guys enjoyed this video. Let me know in the comment section if you did, and I'll see you guys there.